Okay, welcome everyone to this continuation of what is machine learning in mathematics. If you made it this far into the video series, so this is part 10. If you made it this far into this video series, I don't need to tell you anymore that we are doing machine learning in mathematics and not the other way around. So not the mathematics of machine learning. And essentially I want to summarize the state of the arts in 2025. Which is somewhat great and somewhat disappointing. It's kind of in between. So we're definitely not quite there yet in our big goal to replace all mathematicians by machines. And kind of what is missing is a little bit of what missing in this lecture series so far is that I tell you more about all fields of mathematics. Most of my videos so far were focused on like graph theory and combinatorics, because that's where most results are at the moment. I personally think that's because, again, I personally think, I don't have any really good evidence, but because it's kind of easier to do those examples, right? Combinatorics and graph theory is always very accessible. People who are more familiar with neural networks might be more inclined to just do those, right? To just go for graph theory instead of something more kind of pure math, abstract math, whatever type of thing. But there are some results in abstract math as well, and today I would like to tell you about one of them. It's about pattern detection. We'll see what it is. It's kind of very baby abstract math, so in the sense that something you should probably learn in kind of a beginner's class when you're studying. Not necessarily even mathematics, so it's also if you're studying economy or something, you might see this. Depends a bit on the curriculum. Maybe, maybe not. But it's kind of not really research mathematics. That's my point, right? So it's still, all of this machine learning and mathematics is still in a little bit of a baby state. There are some really good examples, and I already had some of them. And there are some, well, this is more like how most papers are. The paper that I'm going to pull up is still really, really nice. So I'm very surprised, actually, that they were able to get these really good results. So the paper I'm talking about is this one. So, and they are clearly very honest. They call it preliminary investigations. Yeah. So we are not quite there yet. But anyway, we go through this paper, and I have one picture stolen from this paper. Anyway, so let's get started. And the story starts with something people like a lot. So I usually like to think in terms of Sudoku, but the Latin square is essentially the same type of thing. So here's a nice example. So it's an n by n array, and you fill in n different symbols. Usually people use just the numbers 1 through 3 up to n, right? So here is a 3 by 3 thing. So 3 by 3 would be 1 to 3, and you do it such that each symbol occurs only once in each row or column. Yeah? And yeah, colors, just whether you think of in terms of numbers or of colors. So here's an example where you think in terms of colors. So here purple, maybe which one is the easiest to see? Maybe light blue. Light blue appears in the first row and column, as you can see, in every column and row exactly once, but never kind of twice in a column or row, right? So Latin square, kind of very. So the picture is stolen here from Wikipedia. Here's a maybe nicer example with ABC. So apparently the name came from Euler using the Latin numbers to fill in the square. But anyway, so Latin squares are around for a long, long time. And here's an example. So A, B, C, and A appears in every row and column exactly once. B appears in every row and column exactly once. And C appears in every row and column exactly once. And then there's some few more examples. And there are quite a few of them. So the number of Latin squares is quite large. So it's bigger than n factorial to the 2n. That's a very large number. The series, the sequences that you can write down on an integer sequence is like, at 8 you have like a lot of them. Yeah? You have a lot of them. And these are just the reduced ones. Oops, what did I do? These are just the reduced ones. And yeah, if you go to the total number at 8, it's just absolutely ridiculous. So in the sense of machine learning, that's great, because then you have a lot of data already for very small values. Yeah. Anyway, Latin square, like a Sudoku puzzle, maybe a little bit more classical than a Sudoku puzzle. So people have studied Latin squares for a long time. So let's come back to the slide. So that's mathematics. Latin squares are clearly mathematics, maybe more puzzling. But here comes kind of classical standard algebra, so algebra, namely groups. KD table, the multiplication tables of groups, right? A multiplication table but for a group. And turns out that they are Latin squares, because essentially the divisibility condition, so that you always have an inverse, tells you that every element has to appear exactly once in every row or column. So here I have two examples of groups of order 4, right? I call the elements 1, x, y, z, and I have two different multiplication tables. And I let you guess for a second which one is which. So the top one here is z mod 4, the first group of order 4, and the bottom one is the client 4 group, so z2 cross z2, right? So both are of order 4, but they have a slightly different multiplication table, and those KD tables are only defined up to permutation, right? So similarly, you could define Latin squares up to permutation, right? So it doesn't really matter in what order your elements come. And it looks really similar. So Latin squares, n by n array filled with n different symbols. Each symbol occurs exactly once in each row and column. KD tables, n by n array filled with n different symbols, colors. Each color occurs once in each row or column. Looks very similar, yeah? But there's one hidden condition. Let's ignore there's also a unit condition, let's ignore that. There's one other hidden condition, which is that the multiplication table for group needs to be associative. Otherwise it's the same. The divisibility gives you this every row and column has each symbol appearing once, and associativity is a bit more of a tricky thing. We'll see that in a second. But anyway, so essentially Latin squares describe quasi-groups where divisibility is exactly that condition, that you have everything in each row or column. So divisibility or invertibility, whatever you want to call it. As I said, I want to ignore the unit, so identity arrow, so I ignore this arrow. So groups are essentially quasi-groups up to associativity. That's the difference. So Latin squares correspond perfectly to quasi-groups, and the difference to a group is just the associativity. So essentially the question is, if you have a Latin square, is it a group? It's like to say, it's asking, does this multiplication table satisfy an associativity rule? Yeah? That's exactly what it's asking. And that seems to be a very, very kind of delicate question. So let's go through some examples here on the Wikipedia page. They have some. If you go to examples, what a surprise. If you go to examples, you see some examples. So let's zoom in and don't read the text. It's cheating. Where's my example now? Now I zoomed in too much and my example is gone. Here's my example. The group of order 1, nothing you can do. The group of order 2, and I kind of recognize the group of order 2. So again, you can just rename your elements, whether you call them x1, x2, or 1 or 2, or blue or red, doesn't matter. So really just kind of the pattern here you see. It's a group of order 2. You can clearly see the swap, right? That's a group of order 2, z mod 2. Here's the group of order 3, and I can actually eyeball that because I have this pattern here. The 1 is here, the 1 is here, the 1 is here, and then the 2 has exactly this 3 mod 3 pattern, and the 3 is here. So that's z mod 3. Here's z mod 4 and the client 4 group. And so again, groups of order 4, and there's only one group of order 5, and that's z mod 5. So they have the one group of order 5 here, so it's one of those two tables, and the other one is just a quasi-group. It's not associative, right? So one of these tables, you can easily see that it satisfies. So the one here appears in each row or column exactly twice, so it's easily seen that this divisibility condition is satisfied. But what about associativity? One of them is not associative. They're not the same here, not quite, right? 4, 1, 2, 5, 3, 4, 1, 5, 3, 2. So they're not quite the same. Which one is not associative? It looks to me like that's like a difficult problem to just eyeball which one is not associative. Right? So it turns out this is z mod 5 and this is not a group. But how can you tell that just by looking at the table? It seems to be a really difficult problem. And the idea is now to train a neural network that can actually kind of detect this associativity in a Latin square. And they were really successful doing that, which I think is like more than 90%. We can actually go, I'm just a bit careful, but we can actually go to the paper and Scroll a little bit down. They do other things as well. So not just the Latin square problem, but the Latin square problem is like easy to understand. So that's why I took it. And here they have a pretty good evaluation, like whatever 90% plus for precision, and Matthews pi is essentially another way to measure precision, and it's really impressive and really good. So they train a neural network that can find groups among Latin squares with a high probability. And if you just pull up this example here again, I'm not quite sure. I mean, this seems to be pretty impressive, right? One of them is not associative, the other one is, and by just looking at it, I've absolutely no idea. I can't tell, huh? But apparently the neural network were able to figure that out, which I think is like really impressive. So it's kind of remarkable. The slight catch is that they only ran it for quite small examples, because otherwise it's just really difficult, right? So anyway, it's pretty impressive. I thought it was a pretty impressive example of how to use neural networks in kind of classical algebra, right? Classical group theory algebra type thing. Right? It's pretty cool. And it was a very plain neural network. Nothing really fancy. It's kind of very nice. And they do many more things. They have a classification of finite simple groups. So classification of finite simple groups, in case you haven't seen that, there are the 24 exceptions, the famous sporadic groups, which in this picture that I stole from Wikipedia, here on the outside. Then there's this huge bunch of groups of Lie type, which is everything here on the inside. Then there's Z mod P for a prime, and the alternating groups, so the symmetric groups if you want. And yeah, so detecting whether a group is simple, that's also what they did from the Cayley table. Again, worked really well with the neural network, which I think is kind of really remarkable. So the classification of finite simple groups, so essentially these are all finite simple groups, is one of the most remarkable theorems of the last century. It's, maybe you've heard of it, the theorem which has thousands of pages of proof. But it's probably just difficult because there are some very small but very pesky examples where you really need to be careful, because somehow this is saying that for most groups it's actually pretty easy to tell whether they are simple or not. So it's a very successful neural network. It's kind of very, I think it's very remarkable. Again, around, if you look at the paper, they have precise numbers. Again, more than 90%. That you just look at the Cayley table, yeah? Look at the Latin square, and you can detect whether it's simple or not, which is kind of really remarkable. Anyway, I hope you enjoyed this video, and I also hope to see you next time.